Saxon Algebra 1, lesson 103. We are going to talk about rational equations. Just a quick reminder, there's a difference between expressions versus equations. The easiest way to tell them apart is that an expression has no equal sign, but an equation has an equal sign. With expressions, we have to keep our denominators. We can't get rid of them. But with equations, we can eliminate our denominators altogether. With expressions, the only way we can change them is to multiply the top and the bottom by the same number. That's all we can do. With equations, we can add or subtract any number as long as we do it to both sides, right? And we can multiply or divide any non-zero. We can't do it with zero. All right, so this is how we can tell them by the way that they look. This is what we have to keep in mind, the limitations, right? Can we eliminate the denominators altogether, or do we have to keep them? And then these are the rules that we can use to adjust them. We just did a lesson on rational expressions. It was 101, I believe. There were no equal signs, and all we could do was make the denominators match and crash them together. But now we're going to talk about equations, and we'll be able to eliminate our denominators all together. So what we're going to do, and one other thing, when we talk about expressions, John tells us to simplify. When we talk about equations, he says solve. This will get to an answer like x equals. With this, we can't. All we can do is just make it neater and simpler, and that's the best we can do. All right? So this is the difference between expressions and equations, which very often gets lost in the shuffle. So every once in a while, I want to slow down and talk about that. Let's look at the first example here. And it's a cute little problem. Right? As algebra problems go, that one's kind of adorable, right? All we see is a y, and then there's 2, 4, and 6 down here. So what we have to do is we can eliminate these denominators. The way that we do that is to find the LCM, the least common multiple, a number that all of these guys can go into. And just looking at this, my brain takes me immediately, this LCM equals 12, right? 2 times 6, 4 times 3, 6 times 2. Then what we do is multiply every term by the LCM, okay? I'm gonna do that with a different color so that it jumps out at you a little bit. Our LCM is 12, so I'm gonna multiply this one by 12, this one by 12, and this one by 12. When I'm multiplying an equation by the LCM to eliminate the denominators, I write it up here at an angle. That's a clue to myself as to what I'm doing. Otherwise, we just have these numbers floating. And oftentimes, we'll be using longer expressions. So I just kind of create this angle up here. Now what we can do is we can cancel the LCM against the denominator. 12 divided by 2 is 6. So these cancel. And then I'm going to have to multiply the numerator by whatever's left over. 12 and 4 cancel to 3. So I'll be multiplying that. I'll put the dots in there this time. I don't do that always, but that's just to help you remember we're multiplying. 12 divided by 6 is 2, so I'll multiply that one by 2. Every term is multiplied, and then we reduce, or we, let's see, what are we doing here? We're going to cancel the LCM against the denominator, right? And that's the magic of the LCM, is that we built the LCM, we built the LCM by looking at all these denominators. And so we know by design, they will all cancel cleanly into it. So that's great news. Let's rewrite what we have here. The denominators are gone. We have 6y plus 3 times 1 is 3 equals 2y. Okay, let's swim this 6 over. That cancels. We get 3 equals negative 4y. And then we'll divide by minus 4. And we get y equals negative 3 over 4. That's the right answer. Notice that because this was an equation, all those things I told you were true. There was an equal sign. We were able, let's see, what were all the things I told you? We were able to completely eliminate the denominators, right? We turned it into just a cute little thing. We were able to use our rules of algebra, right, to swim things back and forth and divide, just like we have. And we were able to solve it and get an answer. Okay, so this behaved like a nice little equation. Let's keep going. They're going to get a little messier looking, but not terrible. The thing I like least about this one is the letters they chose. I don't like the T's. Okay, this has got T's in it. That annoys me. They just look messy, but that's okay. We can live with it. We have a quantity up here, and we have some letters in our denominator. So it does, we've leveled up in a couple different ways, but that's okay. All of our same rules will hold, okay? So the first thing we do is find the LCM. T, 3t, and 3. Okay, so we can only multiply to adjust, but each one of these can find itself in 3t, right? Beautiful. Now let's multiply every term by our LCM, and then we will cancel against and then multiply by whatever's left, right? So 3t and t cancel, and we're left with a 3. Because I'm multiplying by a quantity, I better put that inside of parentheses. 3t and 3t, that cancels absolutely. So we don't have to multiply 14 by anything because it completely canceled. And here we have 3t canceling against the 3, and that leaves us with a t. So I'll put a t there. All right, denominators are gone, and we're now down to 3 times the quantity, t minus 2, we'll distribute that, equals 14 minus 1 times t, t. Okay, we're ready to distribute. 3t minus 6 equals 14 minus t. Okay, let's do a double swim. Let's add the 6 this way. And then let's add the t this way. Okay, so we got rid of those 6's and those t's at the very same time. And we get 4t, right? 3t plus t equals 20. Divide both of those by 4, and we get t equals 5. And there it is, a nice, simple solution to our problem. All of the things I told you about happened. We had an equal sign. We were able to eliminate the denominators, blah, 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 blah. You know. Okay. Another one. There are 6 in all. I want a fresh piece of paper. By the way, the instructions in all of these are telling us to solve, which, as I mentioned, is another hint that you have an equation. Okay, n over n plus 2 minus 3 over 5 equals 0. Okay, don't let that 0 bother you. That's fine. We need to find our LCM. Remember that the only way we can create an LCM is to multiply. So there's no way that we can add like an n to this side. All we can do is multiply these together. Okay? The only way to build an LCM is to multiply. Okay, so all I can do is multiply those 2 things together. Now, you'll see, now my angled thing makes a little more sense, right? Because it's longer, you can see what we're doing. Every term needs to be multiplied. And the plus and minus signs separate the terms, just in case you were wondering what I'm talking about. Plus and minus signs create separate terms. So this is a term, this is a term, this is a term. All right, now I'm ready to cancel the LCMs against the denominators. This cancels against this. We're left with a 5. Sometimes I circle it, and then we write it there. This time the 5's cancel, and I'm left with an n plus 2. And this doesn't cancel against the denominator, but when I multiply it by 0, it cancels. So what are we left with? 5n minus 3 times the quantity n plus 2 equals 0. This used to freak me out. I thought that I was doing something wrong. I wasn't. It's fine. All right, let's distribute. 5n minus 3n minus 6 equals 0. This becomes 2n, and then let's swim the 6. 2n equals 6. And there is a nice, cute solution for us. These solutions have been adorable, right? We got, well, the minus 3/4 was not so great, but we got a 5, and now we have a 3. Lovely, right? Okay, let's do another one. (103.4). Here's another one that looks a little messy. When we first look at these denominators, we go, ugh, how are we going to make these match? Easy, we just multiply them together. So I'm going to write it up here because I have room. It'll be 3n times n plus 4. When in doubt, just multiply them together. I write it up here. And I barely even have to bother here because I know that's just going to go to 0, isn't it? The 3n cancels. And I'm going to have to multiply this times n plus 4. I like when the quantity cancels. And we'll multiply this, 3n, right, the piece that's left. That's what we're multiplying. 3n, and then this is all going to cancel, and we'll just be left with 0. So we have 2 times the quantity n plus 4 minus 6n equals 0. Let's distribute. 2n plus 8 minus 6n equals 0. We'll add our like terms. Minus 4n plus 8 equals 0. Let's kick our 8 over to the other side. We'll live in the negative world for this problem. We'll be crazy. Remember that we can always swim this the way that we're used to it, but there's a special rule that says change sides, change signs. And that allows us to shortcut some of these basic swimming operations. We want to move this 8 to the other side. We want it to change sides. So we know that it has to change signs. So what I can do without showing that as a step of swimming, I can just bump the 8 over and I just change the sign and I know I did it right. And we get n equals positive 2 because those minus signs cancel, don't they? N equals 2. Right? Getting the hang of it. The only thing that's weird is making these LCMs. They're a little awkward, and then we just have to not freak out when we do the canceling. 103.5. Our instructions are to solve. Okay, LCM. Again, it's so tempting to think, well, let's just subtract 2, top and bottom, right? Then they'll match. We can't do that. We can't do that. I wish we could, but we can't. All we can do is multiply. So our LCM has to be x times x minus 2. That used to make me so sad when I first learned this. Are you kidding me? Why can't we do that? All right, so then I'll multiply every term. Whoops. There. The x's cancel, so I'm left with that, and I'll write it here. Here, the x minus 2's cancel, and I'm left with just the x, and I'll write that there. And then we know that's not going to work out for us. So now we have 4 times the quantity x minus 2 minus 7x equals 0. Distribute 4x minus 8 minus 7x equals 0. You getting the feel for this? Oh, I heard you say yes. That was very exciting. Combine the like terms, and let's change sides on the 8. So that will be minus 3x equals positive 8. And we get x equals negative 8/3. This minus sign was clearly attached to the 3. It looks like I put it so it's attached to the 8. What I meant to do is have it floating in the middle. That's the way we typically write our solutions, is with the minus sign floating in the middle. If this wouldn't be wrong, this isn't wrong, but that is the way I would have liked it best of all. Mine kind of drifted up. But that's the right answer. All right? Now, there's one more thing we have to consider in a problem like this. Let me do it in the next one. We haven't been doing it, but I'm going to show it to you now. here's our problem. Whenever we have variables in the denominator, we have to take care that we do not blow up the universe, right? There's always a risk that if we set these values to the wrong number, we could end up with zeros down here. So as part of our process, whenever we start a problem where we see letters in the denominators, we have to say, hold on, they cannot equal 0. So P cannot equal 0. And P minus 4 cannot equal 0. Now, this one's perfect the way it is, but this one we have to do a little bit of algebra to make this look the way we want it to be. We swim the 4, and what we get now is P cannot equal 4. And that makes sense because 4 minus 4, well, that would give us 0. So at the beginning of these problems, whenever you see letters in the denominator, you have to define the unallowable values, right? We have to rule these out and say, absolutely not, we cannot let that happen, okay? We did not do that on all the other problems because I was showing you other things, but I want to add this in now. We always go through and tell what it can't be. So let's go do that. Let's just flip back through these and see how we would do that. This one is fine because it's all numbers, right? It's only letters in the denominators that freak us out. Here we would say T cannot equal 0. And we would say 3T cannot equal 0. Now, again, we'll use a little algebra. And what we see is that this one gets back to the same thing, right? Those cancel, 0 over 3 is 0. So these get to the same answer. T cannot equal 0. All right, we don't have to have a separate one for that, for this denominator. Here, n plus 2 cannot equal 0. So we do algebra. N cannot equal minus 2. That would be part of our answer. This is part of the answer, okay? So we have to include it in order to be right. How about this one? 3n cannot equal 0. And we see that when we multiply, that coefficient doesn't really matter. We just say n cannot equal 0. But here we have this one too, right? N plus 4 cannot equal 0. N cannot equal minus 4. On this one, we have 2 again. X cannot equal 0. And x minus 2 cannot equal 0. Do the algebra, x cannot equal 2. Okay, so that's a part of these problems now. And when you do them in the homework, whenever you see letters in your denominator, make sure that you set up an unallowable, impermissible values, I believe those are called. Impermissible, like the opposite of permission. Impermissible. Okay, so we set these up. Now we're ready to solve. Our LCM is going to be P times quantity P minus 4. Again, it'd be nice if we could just somehow subtract 4 from both, but we can't. This leaves me with a P minus 4. This leaves me with just the P. That all goes away. So we have 4 times P minus 4 minus 3P equals 0. We distribute. oh, look at this. That's going to give us just a single p. And so if we change sides and change signs, we get a very cute and nice little answer. And remember, this is part of our answer. We put those in at the top of the problem. Now, all right, so we do that first, and then we go ahead and solve. That is lesson 103. You now know a whole lot more about solving rational equations. Yay! Goodbye.